acids and what are bases. There's a few properties of each that led to the discovery of each one. It led to the attempt of classifying. So acids tended to be sour. So acids were sour, and they react with bases. And then, meanwhile, bases tended to be bitter. Bitter. They feel slimy. And they'll react with acids. So it was noticed that there were many substances that behaved this way and many that behaved this way, and so people tried to define what are these two things, and they came up with a few definitions. One of the more recent ones is going to be the Lewis acids and bases. A Lewis acid is going to accept an electron pair. So probably the most common version of that one is going to be boron try anything, because boron can be satisfied with 6 valence electrons, but it can take on up to 8. So it can accept an electron pair. So if you have something else that can donate an electron pair, anything with a free one, let's say any nitrogen containing compound like ammonia, it has one lone pair, and it'll donate that lone pair to the boron. So in that case, this is our electron donor, so that's our Lewis base, and this is accepting the electron pair, so that's our Lewis acid. Let's see, same thing. For Bronsted acids, the Bronsted acid donates an H+, and the Bronsted base accepts one. So let's say we have, how about hydrochloric acid, and you have ammonia. When they react, this H is going to be donated by the hydrochloric acid to the ammonia. So we just donated an H+, so we're going to be NH4+ instead of 3. And we're leaving behind that chloride ion. Okay, so this is going to be our Bronsted acid, and this is going to be our Bronsted base. This guy is accepting an H+, and this guy's donating an H+. And then for Arrhenius, Arrhenius is the same thing as a Bronsted, but it has to happen in water, because the Arrhenius definition is that it produces, an Arrhenius acid is going to produce an H+ in water, or produce hydronium ion, and the bases produce hydroxide. So if I put this hydrochloric acid in water, it'll behave as an Arrhenius acid. Let's look. So I had HCl, and I put it in water. This guy donates an H+ to the water, so it ends up making hydronium ion, and still leaves behind the chloride ion. So I can see that that's going to be my Arrhenius acid. So we have these 3 different definitions. If it helps you, you can think that the Lewis is the broadest definition. It encompasses all. And that's because, well, let's start with the Arrhenius. Let's say that we have something that is making H+ in water. So let's start with that HCl. We say that HCl is an Arrhenius acid because we put it in water and it makes hydronium. That's true. It is Arrhenius, so I'm going to put AA, Arrhenius acid. If something is an Arrhenius acid, it's donating an H+ to water. Anything that donates an H+ to water is going to be also a Bronsted acid. So if it's donating to the water, it's a Bronsted acid. If it's donating to something else, it's a Bronsted acid, but not an Arrhenius acid, because the Arrhenius has to happen in water. And then for the Lewis, well, if something's donating an H+, that H+ accepts an electron pair. So if there's an H+ that's moving from one thing to another, that's also a Lewis acid. So Lewis acids are going to be Bronsted acids and Arrhenius acids. Any Arrhenius acid is also a Bronsted acid and a Lewis acid. But if you have a Lewis acid, it's not necessarily a Bronsted or an Arrhenius, and that's because we just have to have the electron pair. So it could be the H+ that's accepting the electron pair, and then we have both of these. It could be an H+ being added to hydronium, and then it's Arrhenius, Bronsted, and Lewis. Or it could just be a substance since that's accepting an electron pair like the boron trifluoride that we looked at. So let's look at some examples. I want to see which species is behaving as each. I'm going to start with the most specific because I know if it's Arrhenius, it's also Bronsted and it's Lewis. So here I have hydrochloric acid making H3O hydronium ion. So I know this is an Arrhenius acid. That means it's also a Bronsted acid and it's also a Lewis acid. And the Lewis acid is the fact that it has this H+, and this H+ accepts an electron pair from the water. So I also know that, let's see, this guy's not making hydronium, so it's not behaving as an Arrhenius base, but it is behaving as a Bronsted base. And it's a Bronsted base because it's accepting an H+ from this guy, and it's behaving as, I know if it's a Bronsted, it's also a Lewis. It's a Lewis base because it has an electron pair to donate. It donates this electron pair to the H+, and that's how it makes this H3O hydronium. And the next one, I have sodium oxide, and we're placing it in water. This is aqueous, actually, and since it's aqueous, this is hydroxide. So I know that I'm making hydroxide in water, so this is behaving as an Arrhenius base. Okay, and then meanwhile, it must also be a Bronsted base, because it's accepting H+ from the water, and it's a Lewis base, because it's donating an electron pair to that H+. So then we look at the water, there's no hydronium being made, so it's not Arrhenius, but Bronsted, it is a Bronsted acid, because it's accepting one of these H+, or not accepting, it's donating one of these H+ to the oxide over here. So it's a Bronsted acid and it's a Lewis acid. And for this guy, I don't have any water, so I know I don't have any Arrhenius. But what I do have is I have an H+ going from the hydrochloric acid over to the ammonia. So since this H+ is being donated, this is a Bronsted acid. And this is a Bronsted base for accepting that H+. I also know that this is going to be a Lewis acid because this H+ accepts the electron pair from this ammonia, and this Lewis base is donating an electron pair to that H+. Then for this next one, well, there's no water, so it's not Arrhenius. And there's no H+ that's moving back and forth, so it's not Bronsted either. My only option is Lewis. And here's that boron thing that we talked about earlier. So this ammonia has an electron pair that it can donate. Since it's donating the electron pair, that's the Lewis base. And if you just remember that ammonia is a base anyways, it'll help you. As soon as you see that something's donating an electron pair and you have trouble figuring out, does the Lewis base donate or accept? Well, ammonia is a base. So, okay, it must be a Lewis base. It's donating the electron pair. Boron is accepting the electron pair, so this is my Lewis acid. My last one, I have sulfuric acid and phosphate ion. Again, well, I don't have water written, so I'm going to pretend this isn't happening in water. So no Arrhenius. And I do have H+ that are moving around, so it's going to be Bronsted. I can see that one of these H+ is going to the phosphate over here. So since this is donating an H+, it's going to be my Bronsted acid. And this guy is accepting an H+, so this is my Bronsted base. And then, of course, this has to be a Lewis base as well, because it's donating an electron pair to this H+. And this has to be a Lewis acid as well, because it's accepting the electron pair.